In this video we're going to look at a few examples of how nature works as a minimiser. Now let's say for example you're walking along the beach, so you're on the land here and you're just walking in this direction and you see someone in the sea and they're in difficulty. So you want to help them. Now what you want to be able to do is you want to go from this point here to this point here, but obviously in order to prevent them from drowning you want to get there as quickly as possible. So in this problem here, you want to minimise the time it takes from you to go from here over to here. Now you might think to yourself that you can do that simply by minimising the distance. So the shortest distance between 2 points is a straight line, so you could draw a straight line from this point here up to this point here. And you might think that this is going to allow you to get to this person in the quickest possible time. But that's not going to be true, because you can run a lot faster on land than you can swim in sea. So you might say to yourself, what I'll do then is I will run to a point further along here. So you go for this point here along to here, and then you can swim up to this point here. So that would mean that you were maximising the length that you run, and you'll be minimising the length that you have to swim. So you might think then that this is a better route to take. It's going to take less time than this route because you can run a lot faster, therefore you're running over to this point here and you're swimming slower, so you've got a less distance to swim, so you've got a less distance. But then you also got to take account the fact is that the actual length of this path here is a lot longer than the length of this path here. So there may be an optimum path between these two in which you can minimise the amount of time that you're actually running and minimising the amount of time that you're actually swimming. So somewhere in between here, there's going to be an actual minimum path of time. So take your time and think about that and imagine yourself actually in this scenario. Now, an extension to this here is something called Fermat's principle. Let's imagine we had a beam of light, and again the beam of light is in the air and it's passing through into water. Now if you've seen before, if you put a stick in water you can see it looks like the stick is bent. So what's actually happening is the light is bending. So the light's travelling from this point here to this point here. Now nature works in a way that the same way that this problem, we worked at this problem here, it works on a path of least time. So the light will travel in such a path as to minimise the time it takes to get from this point here to this point here. So in effect, light is behaving in the same way as we would want to behave in order to minimise the time. So this is called Fermat's principle, and tells you that light travels in such a manner as to minimise the time between 2 points. Now let's look at this problem here called the branchistochrone. Branchisto means shortest and chrone means time. So let's say we start at this point here and we have a ball, and we want the ball to roll from this point to this point here in the least time. So again we can draw a few paths out. We can draw a straight line from here to here, and we can say the ball's going to roll in this direction until it hits this point, and we are going to say, is this the path of the shortest time? Well, you might think that you could actually make the ball go a lot quicker if you were to make the path something like this. This would mean that the ball would accelerate, so it would get up to a high speed at this point here, and then it would slow down as it worked its way along to the end. So we can see here that the ball may well travel from this point to this point in a quicker time. But the question is exactly what path is this going to take, because we could choose a path something like this. In which case it wouldn't accelerate as fast, but the actual path length from here to here would be shorter than this path length. So it would have less distance to travel, but it would also be travelling at a slightly less speed than this path. So again, we're left with this problem: what path is going to be the path of minimal time? Now, a final example that we're going to look at here is the hanging rope. So let's say, for example, we have two little pulleys here. So a pulley in yellow and another one in yellow. And let's say we have a rope. Now I'll just draw this out freehand. So the rope's going to be hanging over the pulley. Something like this. Now, if I was to grab this side of the rope here and this side of the rope here and pull it down the way, then the rope is going to straighten out. Whenever I let them go, the mass of the rope here is going to act so as to pull the rope back down. And it means that the rope will come back down into exactly the same position. Now let's say, for example, I grabbed the rope here and here and I was to pull the rope down again. Then the mass of the rope at this side of the pulley would then pull the rope back up to this position. So there's going to be an optimum position in which this rope is always going to sit, and that's called the equilibrium position. And the question then is, what is that equilibrium position? And how do we work out exactly how that rope sits? And also, why does it sit in that particular shape? Now, it turns out that it sits in a particular shape so that it minimises a particular quantity. Now, in the last examples that we looked at here, we were looking at the quantity being minimised as purely the time. But in this instance here, what's being minimised is the gravitational potential energy. Now, we're not going to get into any detail about any of these examples in this video. We just want to get across the point that nature tends to work in a manner that allows it to minimise particular quantities. Now, the mathematics that we're going to use in order to understand this minimisation is called the calculus of variations. So the calculus of variations is the mathematics of minimisation. So in order to understand analytic mechanics, we want to be able to understand the calculus of variations. Analytic mechanics and the calculus of variations are inextricably linked. Historical problems such as the Brancistochrone, the path of least time for a ray of light, the shape of a hanging rope, these were the catalysts for the mathematics of the calculus of variations. So through the rest of this course, we're going to see how the calculus of variations and analytic mechanics form one of the most beautiful synergies in science.